Hello and welcome to the UK column. Today I am joined by David Siegel, someone who I have been aware of since the mid-90s when he wrote a book called Creating Killer Websites. David Siegel was at that time very much a pioneer of the early World Wide Web and has written a number of books on the topic of the future of the internet and so on, and foresaw many of the things that have actually come to pass. So welcome to the program, David. Now, of course, today we're not talking about the internet. We're not talking about the World Wide Web. We're talking about climate. So let me begin by asking you how you moved from being a tech pioneer to being interested in climate science.
I wish I were still a tech pioneer. You've probably been through the saga of the personal data locker, which I was kind of born to build and never got a chance. So I had to, fill my time with other interesting endeavors, one of which is climate. I've been really interested in the environment. I grew up in Utah, skiing and outdoors. I didn't have iPads in front of my face all the time. I was outside. And in the 80s, I read a lot of environmental books and thought, oh my God, we're destroying the environment. Humans are the problem. We have to reduce population immediately. I used to know Paul Ehrlich at Stanford and had lunch with him many times. And we used to laugh at the silly people like Julian Simon, who said that the Earth is actually doing pretty well and population is not a problem. And we said, no, it's a disaster. It's a bomb. And I was a bit of a disciple of Paul Ehrlich's, to be honest, and Al Gore's. And so in 1991, I took some time off and I wrote this book, A Conversation on Conservation. And there were three parts to it. Why human population has got to go down, why people should become vegan, and why the Earth is being destroyed by CO2. And so I was wrong 100% wrong. Although it was kind of fun to write and produce, I got it all wrong. And so I am one of the people where when I'm wrong, I want to lean into that and find out what I screwed up. And most people are not, as we will discuss. Most people would rather stay away from that. They'd rather be right or think of themselves as right. I want to actually be right about everything. And you know what, Mike? It's hard because you're wrong about almost everything, right?
Yeah.
So you have to swallow your pride and unlearn a lot. And I spent 2015 digging into climate because a friend of mine told me probably I was wrong about that. And and I did. I spent a whole year on it. And since then, I've probably spent about 6,000 hours just on my free time. This isn't my career or anything. It's just something I'm interested in, is understanding how the climate system works. And most of everything you've been told is wrong. Most of everything the skeptics say is probably wrong. There's just a lot of, people not knowing. And I don't know. I'm always just emailing scientists and asking them dumb questions so I can try to be less wrong over time. It's a passion of mine. I have others, as we may discover in future podcasts.
The fact is, nobody really knows at this point. And so the question is, how do you go about pushing a policy when you don't know? So the only way then to do it is to lie. And is that really what we're witnessing? That people that are pushing the climate change agenda are simply lying through their teeth most of the time?
I don't think, because I just don't think they know. I think it's okay they just believe. It's just a religious thing. They just believe. And who needs, you don't need data and logic if you aren't using data and logic to come up with your original position. It's probably, at this point, it's more of an identity issue.
You might say that about the likes of Greta Thunberg, maybe, or people that are campaigning for Extinction Rebellion or people like this. But what about the people that are turning this into a business and a financial enterprise, and people that the IPCC, or people that are taking part at a very senior level at the various COP conferences?
Yeah, it's a really good question, Mike. I did a video you've probably seen on Tom Nelson's channel called Manufacturing Climate Consent. I think most of these people really believe the nonsense they're saying, although the way the UN does things, everything is to decide on the political agenda first and then support it with a bunch of, research, right, and publications and stuff. So that's pretty normal for them. They do it in biodiversity, they do it in health, they do it in a lot of, it's not the most benign peacekeeping organization in the world. So there's a lot of problems there. So it's a dysfunctional organization. So they have to construct narratives and belief systems that work for them. And you know what? The way they measure success is money and power, right? So they're doing pretty well, whether they're lying or not, whether they know it or not, it doesn't matter, because they kind of just go toward the signal. Does it get them more money and does it give them more power?
Yes.
And this has worked tremendously well for guys like Al Gore and John Kerry. I mean, it's just been a fantastic moneymaker. Look at Greenpeace and, all these extinction guys. I mean, it's just fantastic for, once you get the narrative going, it's hard to stop, and it's a great fundraiser.
But in the meantime, of course, it's causing lots of hardship for many, many people as industry gets closed down and developing countries aren't really allowed to develop and this kind of thing.
Yeah, I mean, the tragedy is just, we're spending more than $1 trillion a year on decarbonization, and the suffering has begun long ago. And it's really just a way of moving money from poor people to rich people.
Okay. Well, look, let me bring both of us on screen at the same time, plus your presentation here. So we've got misconceptions of Earth's climate.
Right. So it's easy actually to say that nobody knows much about climate, except I don't agree with that. I think one guy does, and his name is Javier Vinos. And there's another amazing guy named Andy May. And these are both very serious data scientists who are very rigorous about what they know and what they don't know. And this book, Climate of the Past, Present, and Future, is my Bible, because he really lays out the argument with data very clearly, and he easily destroys a lot of myths. And so I spent hundreds of hours with this book. It's 200 pages long. It's very dense. It's amazing, and it really systematically dismantles the atmospheric claims of climate change. And then through other things I've studied, that things about, Tony Heller and Willis Eschenbach, I mean, very, people who are pretty rigorous about, measurement. It's just been clear that it's just mostly correlation is not causation. And nobody talks about causation. They just refer to the IPCC AR reports and don't really read them. But I read them. The people I know read them. I'm part of the CO2 Coalition. Have you mentioned that to people before?
No, we have not.
CO2coalition.org. We are a group of scientists and communicators. One of us has a Nobel Prize in physics. Many of us are atmospheric scientists, and it was started by Will Happer and Patrick Moore, founder of Greenpeace. And it's really an advocacy group to explain that CO2 is good for the world. It is not a pollutant. It is coming out of your nose right now, and it is not going to destroy the planet. There's no cause and effect between just, it's just correlation, the rise of CO2 and the rise of temperatures. It's not even you can pick a better random variable to correlate with, but it's not a good one, but that's the one they chose. And so all of us work really hard to debunk this, and we all have slightly different ideas about what actually drives the Earth's climate. It's pretty interesting, but I believe that Javier Vinos has done most of the work. So I try to explain what he knows. I'm not a climate scientist. I don't have a PhD in anything. I'm a communicator. I read the stuff. I ask dumb questions of scientists all the time. Richard Lindzen is a pen pal of mine, an amazing guy from MIT who was in the original working group 1 of the IPCC. He was one of the people really looking at the science and saying, this doesn't really support your narrative. And so he left the IPCC, as many others have, and is a critic of it. And so we at the CO2 Coalition try to, go up against the Death Star, the Empire, and try to explain that their science doesn't hold any water. And so I want to start quickly, Mike, with just a few things little gems that may help people, because you and I both know that people don't watch whole videos. At least they don't watch mine. So let me just kind of bang out some quick statements that I hope will help frame. The first is that facts and rational arguments don't matter. I mean, you could spend all of your time. I spend thousands of hours on climate science, and no one wants to talk about it. No one, everyone just would rather just attack your credibility. Oh, well, write a peer-reviewed paper and I'll read it. Well, actually, I don't write peer-reviewed papers. I'm a reviewer for a periodical, a climate research paper or a research magazine, and then I curate a list of, I've got 199 peer-reviewed papers on my site, which is climatecurious.com. And all of those have short summaries. So I actually read the papers and try to help people understand that the peer-reviewed science, the empirical science, is on our side and doesn't point to a climate emergency. But the model-based papers outnumber us 100 to 1. So if you're going to do it by number of papers, you can't win that because they're always cranking out model-based, analyses. So facts and rational arguments don't matter. People don't want to talk about climate science. They want to keep their opinions and stay right. It has never been about climate. It has really been about money and power. And even though they don't say it, why would they? We're living in 1984. They're not going to say that, but that's what it's really about. As soon as you counter their claims with any data or logic, they just go sideways and call you names. It's also about identity and tribalism, because people in Los Angeles couldn't, if somebody really spent any time on it and learned that there was no climate emergency, they wouldn't be able to say that to their peers. They would be ostracized. They could lose work. I've lost work. I've lost all kinds of work and friends because I'm not a member of the tribe anymore. I've defected. I must be evil. Another thing to understand is the smart grad students 20 years ago realized that string theory and climate were both places not to go, right? Because these are not science driven. These are agenda driven. And you're going to, maybe if you build a career in either of these two, and probably a bunch of others, you're just going to be doing what other people want. You're not going to be getting to do real science. The smart students are doing physics and geology, which both pay really well, but also critically, the people who pay you to do real physics and real geology are, for example, the physicists all get jobs on Wall Street as quants. They only care about getting the real results of the real world. There is no hidden agenda. They have to be really rigorous in their approach to science. Whereas if you go down the climate science route, you're just going to be doing what other people ask you to do all the time. And so the smart grad students are gone. So the good papers there aren't going to be any good papers. The good papers are written by guys my age in their 50s and 60s because they have tenure or they have some, protection of their life, of their income, and they can feel free to write what they want. Young people can't do that. So there isn't going to be any good climate science coming out of the mainstream academia for a long time until they fix that. The journals are all gatekeepers. You can't say that the peer-reviewed science is the science because most journals won't take a paper that is skeptical or questions the data and the methodology. It's very hard to get published these days unless you're presenting model-based fantasies. And in general, in science, most papers and theories are wrong. It's always been the case. There's really good work on what's broken here, and people don't understand it. So even talking about peer review is a sort of a false, is another belief system that peer review is really science. It really isn't. It's really game. It's really a system that gets gamed. It's all about money. At the scientific journal level, it's all about money. I've written an essay called The Failure of Peer Review, and it really does a deep dive into what's legitimate and what's not. And the whole system is really broken. Roger Pielke talks about this. Many people do. So relying on that is not a good way to do science. And finally, you've probably heard of some reasonable people like Roger Pielke, like Matt Ridley, who's fantastic, like Stephen Koonin. You've probably read his book.
No,
Great,
I haven't read his book. What's
great
his?
guy.
Right.
It's called Unsettled. He was a science advisor to the Obama administration, and he just kind of takes apart the climate models because they're just a joke.
Yeah.
But many people say that yes, there's a little bit of greenhouse effect, and we're causing some warmth, but it's not a big deal. In fact, warm is good and CO2 is good. Yes, we do have to pay attention because if we get much more CO2 in the atmosphere, it could be worse. We don't want that. We have to kind of, but it's not an emergency. And those people are wrong. And I want to show that today because they really mean well, but they're not up to date on climate science. So let's get up to date on climate science.
Right. Just before you do that, just one other
Yeah.
name I'd like to run by you, and that's Michael Crichton. And what's your view of state of fear, for example?
Michael Crichton. Where is he? Where's Richard Feynman and Michael Crichton when you need them most? Maybe we could clone them. Very disappointing that Carl Sagan was so taken by this concept of global warming back in the 80s. That's disappointing. But Michael Crichton was just right on. He's just, the skeptics tend to be, if you're going to bet on anything, bet on skepticism.
Yeah.
Amazing guy. What's the essay? Climate's Aliens. Climate. What is it?
Well, the book is State of Fear, and he includes a lot of the graphs. And although it's a fictional story, it's a story. He includes a lot of the climate science in it, and it seems like a reasonable entry point for a lot of people.
It's so far in the rearview mirror, nobody remembers. But he has fantastic.
Okay.
Climates are made by alien. Climate is an alien. Something you could look up. Phenomenal essay.
Yes.
Richard Feynman is my guy. Richard Feynman is the guy I read to my kids when they're in bed at night. I've been studying Richard Feynman for a decade or more, 2 decades. He says, I'd rather have questions that can't be answered than answers that can't be questioned. But that's exactly what we have today. Censorship and no questions. If you ask questions, you're asking for trouble. You would think that asking questions is a way to engage people and have conversation. No. They have no interest in questions. I ask people all the time. All the time I'm asking people, can we record a Zoom conversation about your beliefs on climate? I just want to ask you a few questions. No one has ever taken me up on that. And I do it every day. I'm just asking, I just want to ask them, why do you believe what you think you believe? Why? Where does this come from? And no one will do that. People will run away from that. Whereas maybe you and me and maybe some of your listeners or watchers will realize that when they're wrong, they want to correct that. They want to lean in and dissect and figure it out and be less wrong. That's only 5% of people. 95% of people do not want to learn. They want to be right and stay right. So I have a proposal for you, Mike, and that is to lead a masterclass in climate science for the silly people who care about the actual science and want to learn how the Earth's climate system works. It's very complex, and I'd like to break it down into several modules, and here are some of them. I'm going to go into a heat today, but I'd like to propose that we put together a masterclass for people who want to really learn, and it would be say a 12 or 16 week class, meets once a week. This book would be our textbook. Javier has written a simpler book called Solving the Climate Puzzle, which we could also use. This is far more technical. And that we really do a deep dive into all these areas and really learn. It's only for the people who are interested. I can guarantee you it's not going to help with your conversations with people because they don't care. Right. But it's fun and it's interesting.
Yeah.
So I would like to propose that we put together this masterclass that meets once a week, and that maybe you could put up a questionnaire for people to say whether they'd be interested in that. And then we'll use the feedback from the questionnaire to see if we can whether we want to put something together.
We will absolutely do that. This is a great idea. And well, I'll be on there for sure.
Yeah. I mean, yeah. So it's a kind of interactive version of what I'm about to present.
Sure.
Right. And this is we're going to do one chapter about heat. And so this is a teaser. This is like a brochure for our possible masterclass. So I hope people will stick around and spend the next, 30 minutes with me learning about heat. And then we'll, kind of wrap up and discuss a little bit more about how the whole thing would look. Does that make sense?
Absolutely.
Right. Now, feel free to interrupt and ask any questions. I mean, you study this stuff, you're interested. So, you're my first student. That's great. Let's, ask hard questions. It's fine.
Do my best.
But we're going to just talk about heat. All right. I'm going to do this mostly in slides, but I also break to do some props as well. Okay.
Yes.
All right. So the first question is, first of all, what is heat? And I'm such a big fan of Richard Feynman that I use his wording because he uses plain English. So heat is molecules jiggling. The faster they jiggle, the higher the temperature. Molecules, it has to be molecules. Okay. If molecules jiggle, you have heat. All right. Most of our heat comes from the sun, right? But how does it travel? It travels through space as light waves. Now, what temperature are those light waves? What is the temperature of space, Mike? What's the temperature of space?
The temperature of space, I would say that space probably has no temperature because there's very little material in space. And therefore, it's only when the energy hits something that it would heat up.
That's right. That's right. Space has no temperature. It's exactly right. Out in interstellar space, far from any stars, there's like 1 hydrogen molecule per cubic kilometer. And only when photons hit that thing is there any change in temperature. There is no temperature in space. So even near the sun, space has no temperature. With no molecules, no temperature. And photons are not molecules. So you'd feel the heat if you were close to the sun. You'd feel it if you were out orbiting the Earth on the sunny side, but that's molecules. That's not space. And the space near Pluto is the same temperature as the space near the sun. Okay? So we call it undefined. We say that space has no defined temperature. So on the other hand, though, if something made of molecules is out orbiting the Earth or out in space, it's going to have a sunny side and a dark side, and the difference between those two can be 500 degrees Celsius, right? So solar energy is very powerful when it hits something and makes those molecules speed up. It just makes no sense to talk about average temperatures of everything. The average temperature, this is Bruce McCandless doing the world's only untethered spacewalk. He has an average temperature of maybe 0 degrees, but it's like 300 degrees on one side and minus 300 degrees on the other side. So average temperatures really do not, in fact, they tell a misleading story about almost anything, especially a planet. On Earth, we have shortwave solar radiation coming in, shortwave. As it starts to interact with the atmosphere, some of it is reflected back to space. That's the albedo. And the rest heats up the molecules it encounters. Eventually, all that incoming energy hits something. Whatever it hits, it causes that thing to warm. It could be clouds. Could be, clouds are like, I think, close to 70% coverage of the Earth at all times. Could be land, it could be ocean, could be water, right? And it causes that thing to warm just the same way that sunlight warms an apple. When struck by sunlight, the apple molecules jiggle more and radiate out long wave radiation, also called thermal radiation. Can you see my pointer by any chance?
No, we could just see the apple and the arrow.
That's fine. All right, just wondering. Okay, good. So these are photons coming in that are high energy and photons leaving. I want to make sure people understand that these are long wave light waves. They are not heat. This is the traveling the speed of light. This is the same thing you would see if you have, night vision goggles. You could be miles away and you could see heat. Well, you can only see heat because you've got incoming long wave radiation coming at you at the speed of light. These are photons. And you see here, this ratio is about right. For every one high energy shortwave photon that hits something, it then absorbs that energy and re-radiates out about 20 much lower energy long wave photons. And they can be many different wavelengths in the infrared spectrum. Okay? When you feel the warmth of a fire, that's actually long wave radiation hitting your molecules and causing your molecules to jiggle, and then you're radiating out. Again, a whole cascade of long wave molecules. So these long wave photons, they don't bounce between molecules. They hit molecules, they get absorbed, and they get re-radiated out, often at a different wavelength. So there's a lot of randomness in direction and in the wavelength that comes back out. And this is happening like 1 billion times a second because it is at the speed of light. All right? Anything light hits will absorb and then re-radiate long wave radiation back out, except maybe a black hole. So we need to track the short wave incoming and the long wave outgoing radiation and the heat. The heat is when it, is the speed added to molecules by these interactions with the photons. All right. So let's just look at the incoming shortwave first. When sunlight hits land, it warms up the land, and the land radiates, as we've just talked about. But the land does not store heat. The land has no capacity to store heat. It stores zero heat. Any heat it gains, it gives up overnight or maybe over a couple of days. It does not sort of build up at all. Okay, that's the land. And the atmosphere transports heat, but it doesn't store it. The atmosphere can store heat in the form of like an inversion layer or a storm, but it doesn't store much, and it doesn't store it very long. So you really think of the atmosphere at equilibrium, and it doesn't build up in the atmosphere. Okay, we'll talk a little bit about how it actually can build up in a second with the greenhouse effect, but it's not constantly building up in our atmosphere. The atmosphere isn't kind of getting warmer and warmer and warmer, and that's what's causing our temperatures. That is not what's happening. It's all pretty much happening in real time. Think of the sun influencing our climate essentially in real time. We're going to get to some exceptions to that, but that's how from the atmospheric point of view, that's how you would think about it, okay? All right, so oceans cover 71% of Earth, and they contain 99.93% of the thermal energy from the bottom of the ocean to the top of the atmosphere. This is kind of a big moment in this talk here where we're going to talk about water. So the oceans have an average temperature of about 5 degrees Celsius. They're very cold and they're very deep, okay? We actually don't know the average temperature. It's probably between 4 and 8 degrees C, because an average for an ocean that has, 20,000 vertical feet, it's first of all, it's a meaningless number. Mm-hmm. Second of all, it's impossible to measure. We don't have the technology to measure that very well. But the oceans store a tremendous amount of heat. They store a huge amount of energy coming in from the sun. Did you know, Mike, that the Earth's oceans, which are, let's say, at 5 degrees Celsius, very cold, contain 4 times more energy than the atmosphere of Venus, which at the surface is hot enough to melt lead, because the oceans are far bigger, and so they contain a small amount of heat, but a lot of it. And the specific heat content of water causes it to be very good at storing heat. And this is really critical to understanding earth science and climate science. So I want to kind of just make this simple, okay? Here's a pot of water in an oven, okay? Put this pot of water in the oven. Turn the temperature to 99 degrees Celsius. That's pretty hot, right? That's 211 degrees Fahrenheit. Let it sit for a long enough time that it comes to equilibrium, right? Now, you can put a thermometer in that oven, and it will read what?
99 degrees.
9 degrees. The air, the racks, the pot, and the water, everything is 99 degrees, right? You can put your hand in there, and it'll be all right, right? You can put your hand in the 99-degree air, and it's okay, right? You can stand it. Now, put your hand in the water. Better not do that.
Yeah.
If you want to get burned, that would be very bad, right? That would really hurt. Forget about touching the metal. The metal sort of represents the land here and doesn't really store that much. But the water is where the heat is in this system. 99% of the heat in this system here is in the water, not in the air or in the pot. It takes 100 times longer or 1,000 times longer to heat the water than it does to heat the air. Okay. The oceans store 1,000 times more heat than the atmosphere. The land stores no heat. All thermal effects are in this ratio, 1,000 to 1. Ocean heat is what drives our climate. There's a tremendous amount of heat moving around the Earth that we'll talk about in another module. But the amount of heat in the atmosphere is trivial. It's negligible. It doesn't even matter if it goes up or down very much because it's not what drives temperatures or climate. This model shows, and it's got a bunch of failings. I understand it's not a model of the Earth, but it gives you the idea that the Earth's climate is driven mostly by the sun, but through the oceans absorbing that energy, storing the heat, and releasing it later. And that's really the story of climate. If you're going to study the climate, you're going to study temperature gradients. Now I want to jump into temperature gradients in a pretty big way now. Okay. So this is the temperature gradient for hothouse Earth about 35, 50, 60 million years ago. Just before the Isthmus of Panama closed in Antarctica, that caused Antarctica to begin to freeze. 33 million years ago was a big step point in our climate. It took a million years or so, but the Isthmus of Panama closed and that reshaped the ocean currents. When the Isthmus of Panama closed, everything changed because before that, water was going around the Earth's equator. I have one right here. Water was going around the Earth's equator when there was the Isthmus of Panama. Whoops, sorry. Here we are.
There we are.
This was all open. And back in the Jurassic, 90 million years ago, all this was open and much of this was open here, through here. This was all open. And so the Earth's atmosphere or the Earth's main ocean currents went around this way and they had no way to move the heat to space, which we're going to talk about. So it was very hot. And so we had a very low temperature gradient from the equator to the pole. Heat was kind of locked into the system and hard to escape. It did escape, but the temperature gradient was very low, all right? Because of the ocean currents. Now then, 100 million years ago, during the Cretaceous, it was a little bit steeper just because of the way these continents were arranged. But still, most of the Earth here was very warm. This is a very shallow gradient, okay? Here's the Earth today. This has a fairly steep gradient that leads to a lot more weather. When you have a shallow gradient, you have less weather because it's the gradient that drives storms, right? It's the temperature differences. You hear that a storm is created when a cold air mass meets a hot air mass. Well, if the cold and the hot isn't that much different, then the storms are less intense, okay? And that the difference between equatorial and polar temperatures creates the need for heat transport from the equator to the poles, something that the IPCC never talks about. And just to go the other way, Here's snowball Earth. Look at this temperature gradient. Very steep, very low. It's about 750 million years ago, and also another one about 440 million years ago. In fact, you and I talked on Twitter about it. Probably driven mostly by the distance to the sun. And the temperature at the equator here, in this case, is below zero. So we have ice at the equator. Now, we don't know this, and I've talked to Chris Gotees about this. He's the expert. We think maybe there were some millions of years with ice at the equator, but also maybe not. There's no way we can really tell. And the poles probably had lakes of liquid CO2, possibly even solid CO2. That's how cold iceball Earth was. The steeper the temperature gradient, the more heat moves from the equator to the pole. Much heat moves out at the poles. The heat moves out, leaving the planet colder. Is this all making sense so far?
Making sense, absolutely, so far, yes.
Now I'm going to put that on hold and come and talk about. Is this all right just to look
Yes.
here? All right, here's our Earth. And the sunlight is coming in parallel lines, right? I do have a pen somewhere, yeah. Coming in, pretty much, straight on, right? At the equator. Now there's a little bit of tilt, right? So something like that. And two things are going on here. There are two gradients, right? First gradient is you got sunrise over here, I think, if I turned around right. I think sunrise is over here and sunset is over here. So it really tails off fast, right? You don't have much heat coming in the early morning or in the late evening, because the peak of the day is when you have most of the incoming energy into the system. Make sense? Maybe I can do it this way. It's a little more picturesque. All right, now then you also have the gradient this way, and this is critical. So you have heat coming in, and if we look at the band of 30 degrees north to 30 degrees south, this is half the surface of the Earth, but it's 2/3 of the incoming energy. The IPCC does not want to talk about this. This should be obvious to anybody. Most of the energy coming into the system is at the tropics. Is there any doubt about this? Is this controversial? Is this an opinion?
No.
No, this is like a bullseye, right? With a square, square function fade, right, in all directions. So it's most intense right here. And by the time it gets to 30 degrees, that's half of the Earth's atmosphere. This is about 80 petawatts, in case anybody cares. And then above 30 degrees to maybe 75 to the Arctic Circle, you get about 40 petawatts for the above and above the minus the negative 30. In these temperate zones, you get about 1/3 of the incoming energy. All right. After that, above the Arctic Circle and below the Antarctic Circle, it pretty much just glances off, right? You just hardly have any incoming, except during summer, you have a little bit of actual warming, but 9 months out of the year, you have no warming because the high energy photons don't even, hit anything. They just reflect off. And the concept that there is some equilibrium here where energy comes in and then goes out through the atmosphere. Yeah, let me show that diagram. All right, there you go. You've seen this diagram. This is a NASA diagram, right? This is just a lie, because this is just all atmospheric in this diagram, that the incoming energy comes here and it just gets re-radiated out as long wave radiation, and the CO2 has some huge effect in clouds, and it's all atmospheric, right? And this is a tiny, tiny portion of the energy exchange, because obviously far more energy goes in at the tropics than can possibly come out. It doesn't. It makes its way poleward and then exits at the poles. And if you don't see that, then you're going to be suckered into this atmospheric argument, and it's going to lead you to read the IPCC documents as though, oh, well, this is all right. No, it's easy to show that it's wrong because this picture is a lie, because the energy comes in here and goes up to the poles and makes its way out. And that's what we're going to talk a lot about in this, master class. So it's all about heat transport. Now, I want to take a minute and talk about the greenhouse effect. This is not the whole module on the greenhouse effect, but this is good. And I think you'll appreciate it, and other people will too. Al Gore says that the CO2, which is 4% of 1% of the atmosphere, is like a blanket around the earth. And you know what? It's true. So I want to explain that. If you're out in the cold and your body is radiating some long wave radiation, but you're out in the freezing cold without a jacket, you're losing heat, right? But if you put on a jacket, what happens? Let's say you put on a jacket that isn't very warm. It's cold, it's outside. You put on the jacket, you zip it up. Now, there's some details here that are important. For a little while, your body is no longer radiating heat out to the atmosphere. Your body is radiating heat into the jacket, right? I mean, jackets don't have heaters unless, you take out any jackets. Jackets are passive, right? What does it do? It blocks the heat. It gets warm itself, right? And it helps trap heat in a particular way. So when we say trap heat, I want to break that down, because if it trapped heat forever, your body heat would warm it up so much you'd be too warm. And you've probably experienced having too warm of a jacket on, too much retention of heat, right? In a cold, and then you're kind of sweaty and cold and the wind, and it's pretty uncomfortable because you have to ventilate the heat. You can't keep it building up, right? At some point, the jacket has to become, in your system with you and the jacket, has to come to equilibrium. And then the amount of heat that your body gives off has to be equal to the amount of heat coming out of the jacket. Otherwise, you'll just get too hot. You'll boil, right? So the recipe here is that it's a function of the amount of heat coming out times the delay, or what we call the residence time. And this is actually what happens with greenhouse gas molecules, whether it's CO2 or water vapor or some other little ones that nobody cares about. But it's the residence time that it increases. So then after it's at equilibrium, then the same amount of heat goes out as comes in. It's not trapping anymore, but it is making those infrared collisions happen a lot more near your body, and then they escape because it's at equilibrium. So then they go. So then still, once it's at equilibrium, the same amount of energy coming in goes out. So this model is correct for that, for your, in the jacket situation. For the atmosphere, the same amount of energy comes in and goes out, and so the more greenhouse gas molecules you have, the more you'll increase the residence time, right? It's the residence time that actually determines the temperature down on the land, okay? But it falls off with a decay function, with a logarithmic decay function, so that after about 100 parts per million, there's almost no effect. It's just minuscule effect after 100 parts per million. And where does all the CO2 come from? Where did the CO2 come from? Any ideas?
It comes from volcanoes. It comes from the sea. It comes from animal life. Yeah.
Close. It actually came from the original atmosphere, right? And then was sucked in. The original atmosphere had much more CO2. And then it, 4.5 billion years ago, right? And then the planet was very volcanic for a couple billion years, and all this atmosphere had tons of CO2. And then it started getting locked up into rocks and going down into sediments and stored, right? And so eventually, when plants came on the scene, they took up all the extra, it was 20% carbon or 18% carbon, 700 million years ago or so. And then the plants sucked it out. and replaced a lot of that with oxygen. So there was a kind of a gradual replacement until that came to equilibrium, and now it's at 400 parts per million. But the first 50 to 100 parts per million do all the work, and all the rest of the carbon doesn't matter. It just doesn't change the temperature of the Earth really one bit. We'll go into that in another module. I just wanted to take a little excursion and talk about the jacket model where residence time counts a lot. Okay, and we already have it. We've had it for 500 million years. Okay, changing it now won't change anything. And one way to see that, Mike, is that, so let me go back to this now. So that there's this incoming solar radiation coming in, and the Earth has to do two things. We've explained that the Earth has to move heat to the poles. No matter what the shape of the continents is, the Earth always has to do that. So it's always trying to find a way. And in 100 million years ago, it did it differently than it does today with the shape of the continents the way they are. You know, when it was 200 million years ago and there was some Pangea megacontinent, it was mostly water, that heat moved differently. Now it works through the specific ocean circulations that we talk about in the Atlantic and the Pacific. Okay, but the Earth has to do something else, and that is keep the nighttime temperatures relatively stable so that we don't all freeze. And if you've been to a desert where it's clear sky at night, you know that it gets very cold at night in the desert. And in the tropics where there are clouds, you get a warm night. You can get a very warm night when you have clouds, and sometimes when you have pressure systems. That is the greenhouse effect. So I want people to remember that the greenhouse effect is responsible for overnight temperatures, maintaining the heat in the system with the residence time so that by morning it's not too cold, or else there wouldn't be any life here. And that the other thing the system has to do is get most of the heat out at the poles. So we have these two things. That is not the greenhouse effect. The greenhouse effect is responsible for overnight temperatures, and it's been about the same for a couple 100 million years since most of the oxygen came and most of the CO2 went away.
So if I'm understanding this correctly, your point here, well, one of the points here is that without the greenhouse effect, there would be no life on Earth.
That's right.
Therefore, the greenhouse effect is not something we should be fearful of, or we should be encouraged to be fearful of. It's a requirement of life on this planet.
Yes, and there's no way it runs away. I'm going to talk about Venus and Mars in a few minutes, but there's no way it can run away. It already did. It's been doing the same. The greenhouse effect has been doing exactly the same thing for a couple 100 million years, keeping life habitable. It can't change. It can't run away. It can't change temperatures on Earth very much at all. Tiny, maybe probably zero. And I'll explain that in another module. All right. I might explain Venus and Mars. We'll see how much time we have. I want to talk about the lapse rate. You see this? You see the diagram now?
Yes. This is familiar to anybody that's been a pilot, by the way.
Right. That's right. Or a mountain climber, a mountaineer.
Yeah.
Yeah. So I want to explain this to the audience. Is that all right? This is going to be a little technical and interesting. Is that all right?
Go ahead.
All right. This is the lapse rate. And I don't have my pointer. You can't see my pointer moving around, right? So we'll just start at the bottom and we'll see that it's at about 15 degrees at the surface, roughly. And I want to explain how this works because it sets the stage for understanding the role CO2 plays in preserving those nighttime temperatures, which is all it does. If you take one thing away from this talk, it's that CO2 preserves nighttime temperatures and makes life habitable. It has nothing to do with our climate or with changes in our climate. All right, so first, this is interesting because NASA always shows the lapse rate going from the land, but most of the world is ocean. So think about the incoming sunlight hitting the ocean, right? There's two lapse rates, right? The first lapse rate is going down, right? We all know that anybody who's been in the water knows that it gets colder as you go down, right?
Right.
So that's just a natural property of the specific heat of water and the currents that don't tend to drive heat down. They tend to drive heat, circulate heat back up. There's layers, right? Same thing. It's the lapse rate. Then on land or in the atmosphere, we have a lapse rate of about, I think it's 7 degrees per kilometer, 7 degrees C.
Well,
but
we're taught it's 2 degrees every 1,000 feet is how we're taught that.
2 degrees every 1,000 feet. I think it's 7 degrees per kilometer, but there's also a moist lapse rate and a dry lapse rate.
Right.
So there's averages, and it can be up to 10 degrees per kilometer and as low as about 4 degrees per kilometer, depending on where you are. Okay. So the atmospheric lapse rate is formed by the warm surface radiating upward. That radiation is long wave radiation, as we've described, and it goes through the physical mass of air, which is mostly nitrogen and oxygen molecules. Those molecules pass their energy to neighboring molecules, and eventually that energy jiggles its way up to space. But at the same time, both water vapor and CO2 play a role not proportional to their mass, because they specifically absorb and re-radiate heat and create this dwell time, this residence time that I spoke about. And on balance, and this is at different frequencies. So CO2 only works in a very two narrow bands of frequency. The rest of it has no has no effect, and I'll explain. That's the Stefan Boltzmann equations, which we'll go to in another unit. But on balance, the thermal and convective transfer of heat via oxygen and nitrogen is actually greater than the greenhouse effect. There's also convection, water or air masses moving up, right? It rises, right? So there are a lot of factors that move heat to space, from land to space, all right? And at the poles, you may not know this because you maybe haven't flown over Antarctica. The lapse rate is negative most of the year when it's dark or cold. It's always cold, but except during just the peak summer months, the temperature goes up as you go up, both North Pole and Antarctica. This is something that the IPCC doesn't like to talk about because CO2 accentuates that. And actually, CO2 works to make the poles cooler. This is technical. I'm not going to go into the details, but you can see on the right in red is just at summertime. It's in August and September, normal temperature gradient showing a lapse rate that looks pretty standard. But the rest of the months, 9-10 months out of the year, there's an inversion, both at the North Pole and very much at the South Pole. It's huge. And that temperature inversion keeps the land cold, and the air is warmed by warm air is coming from the tropics, eventually to reach the pole at a pretty high level in the troposphere, call it 5 kilometers up, because the land of Antarctica is 2 kilometers up, the surface is, most of it. And then it escapes to space, and it actually, all CO2, because there's no water vapor, all CO2 at the poles reverses, because of the negative lapse rate, reverses the effect and acts to cool the surface. Again, very inconvenient. The IPCC doesn't want to talk about. And that's true at both poles. So you really are no way to get some kind of runaway, any temperature change. And there's really no temperature change. All the temperature changes in Antarctica are West Antarctica, where there are 138 active volcanoes. Been going on for, millions of years. So the plateau and the central part of the North Pole, they can't really melt. You'd have to get closer to the sun for them to melt, which will happen, in about maybe 35,000 years or something. Coming back, this is really interesting for you science types. The weather stops at the tropopause, which is that sort of top of Mount Everest, 30,000 feet level. That's where airplanes fly. You're a pilot?
Yep.
You're a pilot. So you know that there's no weather up there. That's why they fly.
That's why they fly there. Yeah.
There's enough oxygen to run the engines, but there's no weather, so it's a lot smoother most of the time. And here, above the troposphere, high energy ultraviolet light is creating and moving ozone molecules. Thank goodness there's an ozone layer, or we would all be cooked. It just happens when normal oxygen molecules get hit by high energy UV photons and, splits them enough that they rejoin into O3 instead of O2. And in the maximum ozone region, we see that there's heat. Why? Because molecules are jiggling. It's actually fairly dense compared to the air above and below it. And that density of molecules with incoming sunlight heats up. But in fact, as you go up above the maximum ozone, this whole stratosphere, like 30 kilometers thick or something, is full of ozone, but ozone concentrates in the 25 to 30 kilometer band, okay? And as you go up, the temperature goes up still. Why?
You better tell me.
You'd think it kind of would follow the profile of the density of the ozone, because that's where the heat is. But no, in fact, what's happening is that those higher energy photons coming in have more energy. So the oxygen and nitrogen molecules they hit them harder and create more heat. There's fewer molecules. It's less dense, but there's more heat per molecule because the energy of the photons is higher.
Right.
Little complicated. That's a tricky one that, graduate students learn. And then again, it goes down when you go up. Well, okay, that's kind of reasonable because you're going up, it's getting much thinner, much less dense atmosphere. And so it gets colder, right? Simply because there aren't molecules, right? So those molecules don't interact with that many incoming photons as they go up. And that's basically true until you get out of space to the thermosphere, when the temperature shoots up and you get very, very hot molecules that can be much hotter than what we have here on Earth. How does that happen? What's up with that? It's a mystery, right?
Right.
Right. So this is the difference. I just think this is really cool. Some people might still be watching who also think it's cool. The 3 or 4 people who are left, it's the difference between temperature and heat. Heat is, when you're out in space and you get the sunny side, your whole, spacesuit or your space station or your planet or whatever heats up because it's a bunch of molecules that is a thing and they all vibrate within, but they don't explode off and leave. Up here in the thermostat, the molecules are very rare. So you might have one hydrogen molecule in, 100 cubic meters. It's very rare. But they're exposed to very high ultraviolet energy. And when those molecules get hit, they get hit hard and they move. And then they get hit there's a lot of photons. There's plenty of photons coming in. They're very high energy. So they get bounced around and they get accelerated to very high speeds. So there's hardly no heat, because there's hardly no molecules. But when you find a molecule, it's going very fast. And it can be 500 degrees centigrade, that molecule. Right. Because it's jiggling and going that fast. And so the thermosphere, and out in the middle of space, if you have any molecules, they can be extremely hot. Out in the middle of interstellar space, they're very hot. There's almost no heat, right? Because there's hardly any molecules. But they're very hot. And that is how you get this W shape here that most people, don't understand. Few people are still with us, but here's the difference between temperature and heat. Now we did that. So now I'm going to go back to this temperature of empty space question. So what if you did have a molecule out in empty space, far away from any stars? Far from any stars. So not very, very dark. Not very many incoming photons. It's rare that a photon hits something, right? Because these molecules are small. So what is the temperature of any molecule? If you stuck a thermometer out in deep interstellar, say in between galaxies, very dark, right? You could just, a galaxy looks like a star at this point, right? A faint star. So if you put a thermometer there, what would the thermometer register?
Well, it can't be any lower than absolute zero, so I presume it's something close to that.
That's what I would think too. And in fact, that's not quite true. It's
okay.
2.7, it's 2.7 degrees because of the cosmic microwave background radiation. You can't get away from it. It's everywhere. And it causes the temperature of anything in interstellar space to be 2.7 degrees Kelvin. That is actually the lowest temperature that a thing can be that's made of molecules in space. Any object far away from any galaxies is going to be 2.7 degrees Kelvin. And that's because this radiation is still coming in, and still the molecule can't go slower than that because it's still being, those photons, those infrared photons from that, the cosmic microwave background radiation are still coming in all over the place, and they keep those objects at 2.7 degrees. Now, last one, quick question: coldest place in the solar system, in our solar system of our sun, where's that?
I don't know the answer to that.
It's fair. I will give you a hint. Okay. It has to be a place where there's no sunshine ever. So Pluto, on the equator of Pluto, it's not warm by our standards, but it's warm by standards of the rest of the objects in the, it's a lot warmer than the cold side of the moon.
Sure.
The warm side of Pluto is much warmer than probably even the cold side of Mercury. Fair? Because it's got a lot of incoming high energy photons.
Right.
They're less high energy out there, but it's warmed up by those photons. So where could the coldest place in our solar system be? It's not Pluto. It's not can't be an asteroid, because an asteroid is going to have a sunny side. Where in the solar system is there no sun ever?
I don't know the answer to that.
It turns out it happens to be, just by chance, on our moon. At the very north pole of our moon, and this isn't true for any other moons, there's a crater called the Shackleton crater. It just happens to be right at the North Pole on the axis. And because of that, the bottom of that crater never sees sunlight. This place is much colder than Pluto. At about 4 degrees Kelvin, it's the coldest place in our solar system, except, in certain laboratories, we can actually make things be, for a small amount of time, we can add a lot of energy and make things colder than 4 degrees. But any rock at the bottom of this single crater is the coldest natural object in the solar system. You'd have to go many, many times farther than Pluto to find a colder place, way into the Oort cloud. So that's just a bunch about heat that you didn't know, I hope, and that is very relevant and sort of forms the basis of our units of our climate workshop or climate masterclass.
Okay, let me ask you a couple of questions then about this. Let's start off with, because we were talking about clouds and the effect of clouds.
Cloud.
What is the effect of air traffic on the amount of heat that's retained within the atmosphere? Because aircraft are generating clouds. Sure. And I see from time to time various people that are that claim to that there is a global warming issue, saying that air traffic helps retain heat within the atmosphere, is contributing to the thing, but that if aircraft were controlled in a slightly different way, and we're flying at a different altitude, and we're therefore not producing persistent clouds, that would help solve the problem. I think it would be a very good thing if aircraft did that, because actually a lot of the time they're blocking out the sunlight, and I would like the sunlight. Thank you very much. But that would be the reason that I would want to see them behave slightly differently. But what do you think is the impact of air travel on climate?
A couple things.
Is there any?
No, but let me just break it down a little bit. In the troposphere, clouds warm the Earth. Clouds have an insulating effect, and sunlight bounces off the clouds, right? Yeah. That's where most of the clouds are. But the clouds increase the residence time of infrared photons dramatically. So your warmest nights are your cloudy nights with low pressure, right? Your coldest nights are the clear, cold nights. In the stratosphere, the clouds are made of ice. The highest clouds are made of ice. And up there with the jet trails, contrails of jets, that's going to be frozen water. And that has a greenhouse effect. Technically, it increases the residence time. Technically, but remember, the greenhouse effect was over a couple 100 million years ago. So adding more anything, water or CO2, to the greenhouse effect doesn't really change anything much. On balance, what percentage of the clouds are in the troposphere? What percent of them are water vapor? Oh, 99.9%, right? So that has a heating effect, and maybe 1% have a cooling effect. Now, remember that almost all the heat going into the system is going into the water. It's 1,000 to 1, right? So not only are you on the wrong side of the equation with jet trails, because there's the jet trails compared to the number of clouds in the troposphere is minuscule. It's not 1%. It's 1% of 1% of 1%. But that's not where the action is. The action is in the water. Heat transporting from the tropics to the poles. That's really what we're going to be talking a lot about in our masterclass. And all of the geoengineering stuff fortunately can't have too much effect. But as you say, I'd rather not have the clouds have the sun blocked if I had a choice.
Right. So then, because we're just about out of time, but let me ask you this, because you talked about when the world was an ice bowl, and you talked about the likelihood being that the reason for that was because we were further away from the sun. And so one topic that really the IPCC doesn't seem to want to go, and climate scientists in general don't seem to want to go near, is galactic radiation, is the solar radiation, the effect of the sun as a driver of the climate.
Right.
And so I don't want to go into very much detail on that at this particular moment, but I'd be interested for you to say something about that, and particularly because obviously we had a period of relative warmth, and then we had a little ice age, as it's known, and so on, and now we're sort of warming up again slightly. And so there are cycles there that aren't really ever discussed. But the question is, how well understood are solar cycles? And I see some people talking about the potential of entering a Maunder minimum at the moment, and so on. And we've just been through a maximum, and so on. And really, this discussion never gets brought into the climate argument. And I think we need to be looking at this a lot closer.
It is a subject for a unit on orbital mechanics and solar effects. So just to give a very high overview, on the scale of tens of thousands of years, pretty much everybody agrees the orbital mechanics dominate, right? The obliquity cycle is 41,000 years, and that pretty much determines temperature on Earth, pretty much. And then the eccentricity, which is the circularity of the Earth's orbit around the sun, modifies the obliquity signal, so that sometimes when both obliquity is I'm not going to overdo this, but obliquity is the angle, right? And when the Earth's orbit is more circular and the angle is more upright, you get the deep cold periods. And when it's more elliptical and more tilted, you get the interglacials, right? And
this is cyclical, is it? This process?
It's cyclical, but it's very tricky because it can skip a beat, because actually Jupiter plays a pretty big role in this stuff, and the Earth is kind of wobbling around and doing different patterns. So it's very tricky. There's nothing repeatable about it, and there are cycles that get skipped. Now that's completely separate from the solar cycle or the sunspots, right? The bottom line on sunspots is they definitely have an impact, but they are not the full driver. They are just part of the input to a very complicated system that has to move heat from the equator to the poles. And that's where all the action is.
Let me say thank you very much for joining. I mean, have you got any sort of final thoughts just to leave us with?
I'd be interested to lead a class for those who are interested. This book of Javier Vinos would be the textbook. It's ridiculously complex, so we'll just kind of break it down and go one chapter at a time for those who are interested. If they are, I recommend that they fill out the form that you're going to put somewhere. Maybe you'll put a link somewhere. And we'll
yes, we will. The link will be in the notes under this video. So yes, absolutely.
Then we'll see if people want to learn the details. It's ridiculously complex. There's not much repetition involved, but I will tell you that the main things that drive the Earth's climate are momentum, which is the solar stuff, plus the plate tectonics, plus the oscillations of the oceans, plus particular properties of water, because water expands when it freezes, and that's really important to our climate. And plus a lot of randomness and variability, which people do not understand. They think that the Earth's climate, they've been told that the Earth's climate was stable at some point, and that we've destabilized it.
Yeah. It's laughable.
It's laughable. It's insane. It's too bad.
Okay. Well, look, David Siegel, I would say thank you very much for joining me today. This has been hugely interesting. We will, of course, do as you suggest, and invite some feedback via form. And with any luck, we will be producing a masterclass in the not too distant future. I'm going to say thank you very much for joining me today, and I look forward to the next one.